By 600 BCE, the pyramids of Giza in Egypt had already withstood 2,000 years of wind and rain, silently witnessing the flourishing and diversification of human civilization. During that era, human curiosity about the stars gradually evolved into systematic research. The Babylonians meticulously recorded the movements of celestial bodies such as the sun, moon, and planets, compiling calendars capable of predicting solar and lunar eclipses. At the same time, ancient Greek began questioning mythological explanations of the world. Based on observed phenomena, such as the shape of Earth's shadow cast on the moon during lunar eclipses, they proposed that Earth might be a sphere. Astronomy was in its infancy during this period. Meanwhile, a star located 2,600 light-years away underwent a massive explosion. Now, 2,600 years later, we have the opportunity to witness that moment in the night sky. Imagine gazing at the stars and suddenly discovering a bright star that was never there before. This is exactly what Berthold, the abbot of the Ulm monastery in Germany, experienced over 800 years ago. He observed a previously faint star suddenly becoming exceptionally bright. What he saw was a variable star in the northern constellation, known as Corona Borealis TCRB. Variable stars are celestial bodies whose brightness changes over time as seen from Earth. TCRB is approximately 20,600 light-years away, meaning the phenomenon we observe today actually occurred 2,600 years ago. Most stars derive their energy from nuclear fusion reactions deep within their cores. However, Corona Borealis Pallialis has passed its prime and is now a white dwarf. Once a massive star, it has exhausted its nuclear fuel and collapsed into a high-density object the size of Earth. Despite its seemingly calm appearance, this white dwarf possesses immense gravitational force, continuously pulling material from its companion star, a red giant. Red giants are aging stars with expanded size and lower temperatures. Toward the end of their lives, they gradually shed their outer layers. This transfer of material is key to understanding Pallialis in Corona Borealis, classified as a recurrent nova. Recurrent novae periodically undergo explosive outbursts. In fact, every 80 years or so, Pallialis in Corona Borealis puts on a spectacular display. As the white dwarf continuously pulls matter from the red giant, the accumulated material builds up on its surface over decades. When the hydrogen gas on the white dwarf's surface reaches critical mass, it triggers a powerful thermonuclear reaction, leading to a dramatic nova explosion. At that moment, the energy release increases TCRB's brightness by 1,500 times, making it visible to the naked eye. The last explosion occurred in 1946, and as time passes, we eagerly anticipate the next eruption. When TCRB becomes a nova, the explosion releases massive energy, ejecting accumulated material at incredible speeds into space, forming an expanding gas shell. This makes the system temporarily one of the brightest celestial objects in the sky. After the explosion, as the white dwarf continues to accrete material, the cycle begins anew. But how can we be sure we will witness this event soon? In its previous eruptions in 1866 and 1946, TCRB displayed a similar pattern. About 10 years before each explosion, its brightness slightly increased, reaching what is called a high state. Then, roughly a year before the explosion, there was a brief dimming. In 2015, the star entered a high state, and pre-explosion dimming was detected in March 2023. This has put astronomers on high alert. The reasons behind these patterns remain some of the most intriguing mysteries surrounding TCRB. But wait, once it explodes, we won't have much time. Indeed, when Pallialis in Corona Borealis erupts, its peak brightness will be brief, lasting only a few hours. Within a week, the star will fade significantly, requiring binoculars to observe it. It is highly likely that an amateur astronomer will be the first to discover the explosion and notify the professional astronomy community. These dedicated enthusiasts frequently monitor the night sky from their private observatories, filling crucial observational gaps. At its peak brightness, the nova will be visible to the naked eye, though binoculars or small telescopes will provide a more detailed view. While it won't match the brightness of the brightest stars or planets, the nova will be an unforgettable sight for skywatchers and amateur astronomers alike. Most importantly, this is a once-in-a-lifetime cosmic event. So, look up now. We've explored the explosive nature of novae, but it's also important to understand how they differ from even more powerful supernovae. There is no better example than the impending spectacular fate of the massive star Betelgeuse. Like most stars, Betelgeuse's core is composed of hydrogen and helium, the lightest elements in the universe. When the core exhausts its nuclear fuel, it can no longer support the outer layers of the star, leading to gravitational collapse. As the star collapses under its own gravity, it heats up and compresses until the pressure becomes too intense. This rapid collapse creates a shockwave, blasting the outer layers of the star into space in a massive explosion, the birth of a supernova. Supernovae release enormous amounts of energy and light, sometimes outshining entire galaxies for a brief period. To put things in perspective, our sun's luminosity, or power output, is about 3.80 times 10 superscript 2 watts. However, a supernova observed in 2015, named Assassin 15LH, reached a peak luminosity of about 2.0 times 10 superscript 3 watts, exceeding the brightness of 500 billion suns. But you might ask, why don't we see it from Earth? Well, Assassin 15LH is in another galaxy, while Betelgeuse is much closer, in our cosmic backyard. This proximity means that a Betelgeuse supernova would be extremely bright, potentially outshining the brightest star in the night sky and remaining visible for weeks. But would it pose any danger to Earth? If a supernova were to occur within a few dozen light-years of Earth, it could have severe consequences, including harmful radiation exposure. The estimated danger zone is around 100 light-years. Fortunately, Betelgeuse is beyond this range, so we are safe. To compare, if a star as close as Alpha Centauri, just over 4 light-years away, were to become a supernova, it would shine as bright as the moon and expose Earth to dangerous radiation. However, Alpha Centauri lacks the necessary mass to go supernova. While other visible red giants could eventually explode, Betelgeuse is the most intriguing candidate. That's why its recent activity has drawn significant attention from scientists. One fascinating aspect of Betelgeuse is its rotation. Recent measurements using the LM telescope array indicate that Betelgeuse spins at an unusually fast rate for its size, completing one rotation roughly every 20 years. This means its surface rotates at approximately 18,000 kilometers per hour, 5 kilometers per second, much faster than Earth's rotation. Such rapid spinning is uncommon for a star of this magnitude and challenges our understanding of stellar physics. Scientists now believe this unusual speed might have a profound explanation. One theory suggests that Betelgeuse may have absorbed a companion star, gaining extra angular momentum in the process, which significantly increased its rotational speed. This event may have triggered intense gravitational disturbances and energy releases, further altering the star's dynamics. Besides stellar mergers, other theories propose close gravitational interactions between stars or the conservation of angular momentum from its original nebula formation. Regardless of the theory, they all point to one common fact: our universe is full of mysteries waiting to be explored and discovered. Thank you for watching. Feel free to leave a comment and discuss.